Hi everyone, I'm Marc. Thanks very much for checking out this video. This is joint work with Bressan and Matthias Lanzinger. If you take a look at the title, you will see this will be about the complexity of counting copies of small directed graphs in large directed host graphs that have small Outdegree. But first things first, let me set up our problem. So for subgraphs given H and G, given graphs H and G, I will write sub from H to G as the set that contains all subgraphs of G that are isomorphic to H. I might also call the elements of this set the copies of H in G. For example, if this is H and if this is G, then those three would be examples of copies of H and G. And essentially, we are interested in the complexity of evaluating this function here. So I will add this sharp here and substitute G by the star for the function that expects as input a graph G and then outputs the cardinality of this set. That is the number of copies of H in G. For induced subgraphs, we use almost the same notation. So I will write in sub from H to G for the set of induced subgraphs of G that are isomorphic to H. And I will also call the elements of this set the induced copies of H in G. If we take a look at the same example as before, the first two here are also induced copies of H, but not the last one because we have additional edges here. And again, I substitute G by the star and add a sharp to denote the function that maps an input G to the cardinality of the set. That is the number of induced subgraphs of G that are isomorphic to H. Now, think of H, for example, being a complete graph of size k. Then evaluating this function here is the same as counting k-cliques, which is known to be a hard problem. And the overall goal of this line of research is to find out which instances of those counting problems are actually tractable. One very successful method that was analyzed a lot in the last 10 years was the restriction of the patterns. So formally, given a class of graphs, which I denote by the calligraphic H here, we would define sharp sub of this class and sharp in sub of this class as the problem that expects as input a pair of pattern in this class and an arbitrary graph G. And then the goal is to output the number of copies of H in G or the number of induced copies of H in G. And let me emphasize that the class is part of the problem definition, not part of the input. So every class defines another counting problem. And again, if this class would be the set of all complete graphs, then both problems would actually be the same as the counting clique problem. And intuitively, the goal is to find out for which classes those problems are efficiently solvable. I only vote tractable here because I don't want to say polynomial time tractability. I want to relax this notion a bit. We assume in this line of work that the pattern is significantly smaller than the host. So what we do is we parameterize the problem by the size of the pattern. And then our question for tractability becomes fixed parameter tractability. So we aim, now I can formally state you like kind of the main question here, for which classes are those problems fixed parameter tractable given this parameterization? That is, for which classes exists a computable function f such that we can solve those problems in time f of the parameter, that is f of the size of the pattern, times the polynomial in the host. And f might be any computable function. It might be super polynomial or even exponential. And the idea is, well, if h is really significantly smaller than g, then this might still yield an efficient algorithm. In this setting, this question has actually already been answered. A line of research due to Kotikapi and Dell and Marx proved that for the subgraph counting problem, this problem becomes fixed parameter tractable if and only if the class has what is called bounded matching number. Here, the matching number denoted by M is just the size of a maximum matching of a graph. And if this is bounded by a constant, then the problem is FPT, and otherwise it's hard. So it's hard for the class sharp W1, which you can think of accounting parameterized counting equivalent of NP. And we also get like an almost tight lower bound under ETH. We say almost tight because if we remove this lock here, then this is essentially saying that you cannot beat the brute force algorithm. For induced subgraphs, there's like a similar result is known, but the tractable cases are even more restricted. We know that here the problem is only tractable if the class is finite. And this is trivial in the sense that, okay, if we know that there's a constant upper bound on the size of elements of this class, which we have since it's finite, then the brute force algorithm is already FPT. And again, in all other cases, we are hard. And we don't only have this almost tight lower bound here, we even have a tight lower bound. So unless ETH fails, this says that the brute force algorithm is optimal. And I want to make now 2 points with this slide. First, in this setting, we understand the problems pretty well. And also, we understand that they are inherently infeasible. Especially for induced subgraphs, we basically only get that the trivial instances are tractable. So we would like to do more. Okay, we restricted the patterns, and now the obvious next step would be to also restrict the host. And one like very prominent restriction of the host classes is to consider degenerate graphs. So I want to emphasize on degenerate graphs in a bit more detail because the recent search on works on counting in degenerate graphs is kind of one of the main motivations of our works. So let me spend a slide on this. Let me start with defining what degeneracy is. We say that a graph has degeneracy at most D if it can be totally ordered such that every vertex has at most D neighbors that come later in the ordering. Equivalently, this means that the graph has an orientation such that every vertex has Outdegree at most D. So this graph here, for example, has degeneracy at most 3. And when I said orientation, I actually mean acyclic orientation, of course. And very roughly, like having small degeneracy generalizes having small degree. And in contrast to small degree, this notion actually captures sparsity in real-world networks often quite well. There has been lots of work done in pattern counting, that is subgraph and induced subgraph counting in degenerate graphs. One classical result is due to Shiba and Nishiseki. They proved that you can count cliques in linear time if the degeneracy is bounded by a constant. Their approach was greatly generalized in quite recent work by Bressan. I won't go into the details here because we don't need the details for this video. But essentially, Bressan gave an algorithm that can count homomorphisms from a graph H into a degenerate graph if what is called the so-called DAG tree width is small. DAG tree width is kind of a tree width version that works well for directed acyclic graphs. But in a nutshell, this is just like a generalized version of the Shiba and Nishiseki algorithm. And then independently, about 2 years ago, Gishpolina, Levantsov, and Shapira, as well as Bera, Pajanasanghi, and Seshatri, they asked the question, when can we count subgraphs and induced subgraphs in linear time in degenerate graphs? And they gave an explicit criterion. So they answered this question completely. And so this solved linear time versus nonlinear time. And together with Bressan 2 years ago, we also answered the question about a fixed parameter tractable versus non-fixed parameter tractable pattern counting in degenerate graphs. Okay, so we now understand pattern counting in degenerate graphs quite well. But the point I would like to make here that the common theme of the upper bounds in all of those works is the following. So the algorithms always compute an orientation with small out degree, which of the host, which exists because we know the degeneracy is small. Then they guess the orientation of the pattern, and then they actually reduce this to a directed pattern counting problem. And it turns out that the directed pattern counting problem to which all of those results reduce is not classified yet. And this is what we did in this work. So now given direct graphs H and G, we would like to count the copies of H in G, and we parameterize the problem not only by the size of H, but also by the out degree of G. Okay, so we assume that both the out degree of the host and the size of the pattern is significantly smaller than the size of the host. And again, our goal is to find out precisely for which classes of patterns this problem becomes FPT. And this might be surprising at first glance. The tractability criterion is not the same as for degeneracy. So there's actually lots of stuff going on in the directed setting. And of course, we also consider the induced version, but the induced version is kind of a more simpler version to analyze than the not necessarily induced version. So I will emphasize in this video just the not necessarily induced version, that is counting subgraphs. Okay, there are like many technical steps in our analysis of the problem, and in this video I will just give you like an overview over everything. Okay, so let us start by counting subgraphs. So keep in mind now our setting is we're given a directed graphs H and G. H is much smaller than G, and we would like to count the copies of H and G. And we also know that G has small out degree. And what we do in the first step is to express the number of subgraphs as a so-called linear combination of homomorphisms. So we translate this problem in, this is sometimes called the homomorphism basis. So let's take a look at this, what this means. So the function that counts copies of H in an input graph can equivalently be expressed as a finite sum over directed graphs. Recall we are in the directed setting for like a coefficient of this directed graph times the number of homomorphisms from this directed graph into our input. And here homomorphisms between directed graphs are just mappings from vertices to vertices that are arc preserving. So whenever I have an arc AB, then the image of this arc must be an arc in the host. And we know that this expression is unique. So this linear combination is unique. Now you might ask, okay, why would we do this? Why would we translate our subgraph problem into this linear combination? And the reason for this is, and if you have following like parameterized counting in the last couple of years, this is not surprising to you. But yeah, this is again what is called the complexity monotonicity principle, which was independently discovered by Chen and Mengel and Kotekapi and Dell and Marc. And in a nutshell, it tells you that first, if you can compute all terms in this combination with a non-zero coefficient efficiently, then you can compute the entire linear combination efficiently. Okay, so that's not very surprising. That's trivial. But the other direction is the interesting one. The other direction tells you that if at least one homomorphism term is hard to compute, then the entire sum is hard to compute. And this is a very unique property to homomorphisms. So for example, if you would count the number of satisfying assignments plus the number of non-satisfying assignments of a Boolean formula, this would always be 2 to the number of variables. So this is easy. But each individual term, the number of satisfying assignments and the number of non-satisfying assignments, are both hard. So in this example, we don't have the property of that the linear combination is hard if a term is hard. The very special property of homomorphisms here is that here we have this very nice property. And it was observed by Gishpolina, Levantsov, and Shapiro that this principle remains true in the degenerate setting. And we show in this paper, and this is actually a quite easy proof, that even in the directed setting, and even if we parameterize by the out degree, this framework, this principle still remains true. Okay, so what does this mean? This means, given that we have this property, to understand the subgraph counting problem in directed graphs, we have to understand the homomorphism counting problem in directed graphs. There's no way around it. Okay, so let's take a look at this. And again, as I said before, I won't go into the technical details, quite a lot of them. I will more like give an overview, but feel free to talk to us during the conference. Imagine you're given this directed graph H, and we are first interested in the sources of H. Here, a source is just a strongly connected component that has in degree 0. And those 4 are precisely the sources. So just to let me say that again, the source of a directed graph in this context is a strongly connected component within degree 0. And if we identify the sources, we can associate each directed graph with what is called the reachability hypergraph, denoted by R of H. And the vertices of this reachability hypergraph are the vertices of our graph. And for each source, we add an hyperedge containing all vertices that can be reached from this source. So for example, this source here, from this source, we can reach, of course, the source itself, this vertex, and this vertex. Then if we take a look at here, we have this source, those two vertices here, and this one. So this back here, this hyperedge, is precisely containing the vertices reachable from this source. And we do this for each source. And indeed, we found out that the structure of this reachability hypergraph is very tightly linked to the complexity of counting homomorphisms from this graph. Formally, we do the following. We can reduce the homomorphism counting problem from this graph to what is called a counting constraint satisfaction problem from this hypergraph. I will use counting constraint satisfaction problems, also called sharp CSPs, only in a black box version here, so I won't go into the details. The only thing you should keep in mind is that in the counting in the sharp CSP problem, this problem depends like solely on the hypergraph of the instances. Okay, so let's collect that. So I quickly want to recall those two results here, like the linear time algorithm for counting k-clicks in degenerate graphs and the DAG tree-width-based algorithm. And I just want to point out that we found out that reducing the homomorphism counting problem to sharp CSP and then invoking known results for sharp CSP is again just the generalization of those two. So in some way, this is like the most general way you can think about this, like a homomorphism counting problem in degenerate or in directed graphs. Okay, and now the very nice thing is that counting constraint satisfaction problems are very well understood. I told you before, the complexity depends on the hypergraph, and more precisely, we know that those problems, sharp CSP, becomes fixed parameter tractable if the fractional hypertree width is small. If you don't know what fractional hypertree width is, don't worry. Again, we will use it just as a black box. The point is, we understand the complexity and we have like a concrete measure of a hypergraph that tells us the complexity. Okay, so what does this mean for our problem? So first, for our algorithm, what we will do is if we want to count subgraphs, copies of H in a directed graph G, we go into the homomorphism basis, and then we translate each homomorphism term into an instance of sharp CSP. And if all of the reachability hypergraphs have bounded fractional hypertree width, then the problem, this algorithm is an FPT algorithm. And if we find at least one term that is hard to compute, then complexity monotonicity tells us that the problem is hard. And those two actually suffice to fully understanding the problem. So essentially our message is that the reduction to sharp CSP is optimal. So assuming ETH, this reduction to sharp CSP is the best you can do. Those are all FPT cases you get. So let me give you now our main theory. Okay, so given a directed graph H with k vertices and a directed graph G, the host, of Outdegree D, then we can count copies of H and G in the following time f, some computable function of K and D, so the size of the pattern and the outdegree of the host, times the size of the host to the fractional cover number plus a constant. Okay, so what is the fractional cover number of a directed graph? It is closely related to the fractional edge cover number. Let me go back to a directed graph H and the reachability hypergraph of H. If you delete the sources from the reachability hypergraph, you get this hypergraph here, which I'll just call gamma. And then the fractional cover number of our directed graph is defined to be the fractional edge cover number of this hypergraph. If you don't know what fractional edge cover number is, it's like a well-established invariant on hypergraphs, and it applies here. But then again, we only use it as like a black box here. Okay, and what we then actually show is that if our graph H has small fractional cover number, then all terms that survive into the homomorphism linear combination will have small fractional hypertreewidths. So this is like the main technical point of our algorithm. Okay, so let's go back to this slide. Let's take a look at two examples. If our pattern is a union of triangles that are cyclically ordered, then you can prove that the fractional cover number of this graph is actually 0. So we will get size of G to the O of 1. So we will get an FPT algorithm. But if each triangle is oriented acyclically, then the fractional cover number will grow with the number of triangles. So this would be, here the algorithm would not be an FPT algorithm. Okay, and this means that even like by a slight modification, we can get from a very easy instance of the problem to a very hard instance. And now this is what I promised you before. This, when it comes to FPT versus non-FPT, this is optimal. So whenever the class of allowed patterns has unbounded fractional cover number, then you cannot be FPT unless the exponential time hypothesis fails. Okay, so this is our main result for counting subgraphs, and I'm running out of time, but I just want to quickly mention that we get like a similar classification with a slightly different criterion also for counting induced subgraphs, and the analysis is actually much easier for induced subgraphs. Okay, but yeah, this was everything I wanted to show you in this video, and feel free to talk to us at the conference if you have more questions. Thank you very much for watching. Goodbye.